Hello everyone, my name is Song-En Zhang. In this video, we will introduce our paper, Mix and Match, a novel FPGA-Centric deep neural network quantization framework. We are from Northeastern University, the University of Hong Kong, and University of Southern California. Briefly introduce myself. I'm a third-year PhD student at the Northeastern University, Corey College of Computer Science. My advisors are Professor J and Professor Wang. My research focuses on deep learning, hardware and software co-design, model compression, and DNN quantization. Nowadays, deep neural networks have achieved extraordinary performance in so many applications, such as computer vision, self-driving, speech recognition, and healthcare. However, the state-of-the-art DNNs may require up to gigabytes for model size and a 10-squared gigaflow point operation for inference computation, making it a challenging task to perform on-device inference. To address this issue, this paper will focus on model quantization, which becomes imperative to the DNN hardware acceleration, especially on the FPGA and ASIC platforms. Weight quantization can be considered as a mapping from 32-bit float point weights into n-bit weight representations. By representing weights with fewer bits, weight quantization can directly simplify the implementation and accelerate the inference execution speed in a hardware-friendly manner. Also, there are several types of quantization. Binary and ternary quantization use extremely low precision for DNN models, with weights constrained to -1 to 1. Multiplications can be replaced by additions. However, binary and ternary introduce non-neglectable accuracy loss. For example, based on reports from above works, accuracy typically decreased by more than 5% under binary scheme, and 2 to 3% for ternary quantization. Thus, the fixed-point quantization scheme applies the modest and the flexible quantization rates to preserve the accuracy, but still needs to use complex multiplication. Power of 2 quantization replaces multiplication by bit-shifting operations, but its precision cannot be increased effectively with increasing the bitwise, because increasing the bitwise will merely increase the resolution around the mean, while the tails are still in low precision. Thus, in this work, we propose the sum of power of 2, naming SP2, formally the quantized weight values by the SP2 scheme with a total of n-bit representation in this equation, where Q1 and Q2 are power of 2 numbers as the quantization levels, and M1 and M2 are the number of bits to represent the power of 2 numbers. Please note that with the total of n bits to represent an SP2 quantization weight value, 1 bit still need to be reserved for the side bit. Then, compared with fixed-point quantization, power of 2 quantization, what is the sum of power of 2 looks like? Here, we show the weight distribution of the force layer in the MobileNet V2. Along the x-axis, we label the quantization levels by fixed-point, power of 2, and our sum of power of 2 quantization schemes. First, let us understand the intuition why the power of 2 quantized model incurred a non-negligible accuracy degradation, while SP2 and fixed-point quantization models can achieve similar accuracy performance. The power of 2 scheme has very high precision around the mean, with only 4-bit weight presentation, but the tail ends present very low precision. In contrast, our SP2 quantization possesses relatively evenly scattered quantization levels, which is close to that of the fixed-point quantization levels, except the tail ends where very few weight values are presented. This explains the advantage of SP2 quantization scheme. However, only use SP2 is not enough because SP2 only uses LUT of the FPGA. Thus, we further propose the mixed scheme quantization, which is to partition DNN weights in the same layer into 2 categories. One is handled by fixed-point quantization, and the other by SP2 quantization. This figure shows that the weight matrix be obtained by transforming the weight tensor of the layer into a 2D matrix with row and columns. For rows with more Gaussian-like weight distributions, SP2 quantization can fit better, while for rows with more uniform-like weight distributions, fixed-point quantization should be used. Thus, the mixed scheme can achieve similar or even potentially higher accuracy than existing schemes. So in this table, we show the accuracy results, which are compared with different quantization schemes. Take the Resonance 18 as an example. We can see in the CIFAR 10, CIFAR 100, and ImageNet datasets, the accuracy of the sum of power of 2 and fixed point quantization scheme are very close. That is because SP2 can give relatively even interval than the vanilla power of 2. Further, MSQ makes the quantized DNA weight fit the original weight distribution better. The hardware framework contains 4 modules, as shown in this figure. The major computation components are the general-purpose matrix multiplication, which is GEMM cores. There are 2 heterogeneous GEMM cores, GEMM fixed for conventional multiplications, and the GEMM SP2 for SP2 operations. The detailed workflow of 2 GEMM cores is illustrated in this figure. The GEMM fixed core is composed of multipliers implemented with DSPs on FPGA, while the GEMM SP2 uses LUTs to realize shifts and addition for the novel SP2-based computations. So the on-chip resources should yield a particular ratio of design parameters, which is the key motivation of this work. Then this figure presents the resource utilization with different implementations. Apparently, with the size increase of GEMM SP2, more on-chip LUT can be leveraged for the better peak throughputs. To be more specific, we progressively increase the size of GEMM SP2 core till the LUT utilization reaches 70%. To demonstrate the improvement of the proposed MSQ scheme in the hardware aspect, we implemented the architecture with heterogeneous GEMM cores on the embedded FPGA device. As this table shows, we implemented the architecture on the 2 devices with different design parameters that result in different throughputs and resource utilization results. We set up different ratios between the PE array size of the GEMM fixed and the GEMM SP2 cores. To present the performance with real-world applications, we employed different CNN and RNN models with the proper SP2 fixed-point ratios on the 2 devices, compared with the design with only 4-bit fixed-point quantization. The optimal design on XT7Z020 increases the throughput from 36 to 77 GOPS for a Resonance 18, and the optimal design on XT7Z045 increases the throughput from 144 to 359 GOPS. Thanks for watching this presentation. Please contact us if you have any questions. Thanks.